Welcome. In this session in linear data analysis, we'll explore linear regression as a problem of projecting a vector to a vector space. Let's consider a problem that is very often posed in linear data analysis, and this problem is called ordinary least squares. And in some courses that is abbreviated. We won't need that abbreviation. So the idea is to minimize, and this is a technical term, an objective function of the error. And by that we mean, when we say objective function, it means it maps a vector input to a scalar output. And here our vector input is the weight vector W. So the squared error is the one that's most often used. And the squared error is, this will often be written as error 2. So that's because it uses the L2 or Euclidean norm. And that is defined as we take the ith error and we square that ith error, and then we sum over I for all of the observations that are present in the data. And we know that if we take the sum of the squares, that is the same as saying, let's gather these individual errors into a vector, and so we'll call that vector E, and that vector E depends on the parameters of our model, and the sum of the squares is equal to the squared norm of the error vector. Now, we've come across this already, and that idea was that so this is the origin. We always have to have the origin. When we had a vector space, which we write as double-barreled V, and we had a vector C that was given, what we did was we projected this, and the error vector was the difference between the vector that we were given and the vector space. And E was in the orthogonal complement of this vector space for the bigger vector space that it was living in. So the geometry of this, the geometry is that we want a vector E with the smallest norm. Strictly speaking, the smallest squared norm, because that's how it all works. And the reason it's called ordinary least squares is for two reasons. One is it uses the squared error, and the other is it's ordinary. And we need a linear model of our data. And what we'll say is that this function that uses all of those data and uses our parameters. Now, when we write this semicolon, what we mean is this first part in our case is fixed, and this is the interesting part. This is varying. And we'll define that as, we'll say that this is observation 1 times weight 1 plus observation 2 times weight 2, and so on until we've represented all of the observations that are available to us. And that can be, we can gather the A terms into a vector, and we can gather the W terms into a vector, and that is just A transpose W. And so if we have a linear model, so for each observation we have this, and then the observation residual error is, we'll say that EI of W, so now we are saying that we'll define that as being the difference between the ith dependent value and the model, the ith observation, the model of it. And when we gather all of the errors into a vector, we gather all of the dependent data into the vector, we gather all of the independent data into a vector, and we're saying that the error vector that depends on our model parameters have to be the collected dependent observations minus our model of the data. And our model is, we'll take the data as usually a tall thin matrix and we'll multiply it by our weight vector, and that will give us our model. And then we take the difference between the observed dependent values and our model, and that is our error. And that is exactly what we were doing when we did projections. So that means that we can use the projection. So solve as, we'll say that we're going to project the vector C to the vector space V that is spanned by the columns of A. And we already know how to do that. And that is, so the solution for us is the normal equation. And that is, we take the data that are gathered together in matrix A and we pre-multiply it by the transpose, and that is a symmetric positive definite. If the data are, if the columns of A are linearly independent, then A transpose A is full rank, it's symmetric, and by construction it's symmetric positive definite, and we multiply that by W, and that gives us A transpose C, and we can solve this linear equation for the weights. And so we see that the problem of linear regression, which is minimize the sum of the squares of the individual errors, is the same as a projection problem that we solve geometrically, and we know that that solution is the same. So linear regression by ordinary least squares is the same as orthogonal progression.